Hello everyone, let's take a look at our next problem. If n is a perfect square and its second last digit is 7, what are the possibilities for the last digit of n, and can you show this will always be the case? Okay, so we need to think about perfect squares mod 100 because we're concerned with the last two digits of the number. I don't really want to write out every single square mod 100. Although that would almost certainly end up solving the problem. I'm going to change a little bit the way that the question is worded. I'm going to let n be an integer, and n squared, of course, is going to be the square of that integer. And I'm just going to continue. I'm just going to write out the first few here and see what kind of pattern we can extract here, if there's one at all. So the first thing that I note is that for the first 10 squares, none of them have a second last digit of 7. And in fact, I wonder, is that going to continue? So the first 20 perfect squares never have a second last digit equal to 7. Is there a pattern in the second last digits? 1, 2, 3, 4, 6, 8, 0, 2, 4, 6, 9, 2, 5, 8, 2, 6, 0. Perfect square, second last digit is 7. The possibilities for the last digit. So I've continued the pattern all the way down to 30, and I did find two perfect squares where the second last digit is a 7, and they both end in a 6, which is interesting. I wonder if 49 squared and 51 squared have a second last digit of a 7. They do not. What is so special about the second last digit being a 7? So I've continued all the way down to 40. There's no other sevens, but I did try something kind of random, and I showed that 76 squared is 5776, which is kind of interesting. What if I write my number n as 10m plus k and compute n squared? And I want to think of this as being a representation of the number in base 10. So I have 100 m squared plus 10 times 2mk plus k squared. But, this number could potentially be greater than 9. And this number could be greater than 9. Well, this will be greater than 9 if k is greater than 4. Let's think about the cases where this kind of works. So if k is 1, 2, or 3, then this will be the ones digit. That puts a limit on what m could possibly be. Okay, let's break this into cases. Let's try k equal 1. See what we get. Ooh. So m we're doing everything mod 100 here. We only need to write out the first 100 squares. So m is between 0 and 9, and k is between 0 and 9. So can this, so if 2 times n, if this is supposed to be the second, okay, 2 times m is always even. And this, when we add this digit, it never carries over. Yeah, so k cannot be, if k is 1, 2, or 3, we can never have a 7 here. If k is 2, then I have n squared is equal to 100 m squared plus 10 times 4 times m plus 4. And again, the 10 digits will be even. And if k is 3, I have n squared is equal to 100 m squared plus 10 times 6 times m plus 9. And again, the tens digit will be even. So now let's think about larger values of k. K is equal to 4. I have m squared is equal to 100 m squared plus 10 times 2 times m times 4 plus 16. And so the tens digit, this turns into 100 m squared plus 10 times 8m plus 1 plus 6. Okay, so what values of m could we end up with here? If this is going to be a multiple of 7, Well, m would have to be 6, right? Are there other... But does this correspond to our... do we end up picking out... Wow, why can't m be 2? Oh, no, because this is k. Wait a minute. I have 2 and 4. 24 squared gives 576. Do I have an arithmetic mistake somewhere? Okay, hold on. N is equal to 10m plus k. Then n squared is 100m squared plus 2 times 10m times k plus k squared. Oh, I don't need this to be a multiple of 7. I see my mistake. I don't need this to be a multiple of 7. I need the last digit of this to be 7. Yeah, okay. So this thing here is wrong. Okay, so 8m plus 1 has the last digit 7. Means 8m has the last digit 6. And if we think of all the multiples of 8 that have a last digit of 6, we have m is equal to 2 or 7. So let's check. So if k is 4, the last digit is 4, so 24 squared we already know ends in 76. What about 74 squared? Yeah, cool. 74 squared is equal to 5476. So, we end up with 76 again. Okay, so let's go through. I think continuing like this will probably get us there. So let's now think about when k is equal to 5. N squared will be 100 m squared plus 10 times 2 mk plus 25. And here we see, okay, well, let's expand this. This will give us 10 times 10 m plus 2 plus 5. And we want the last digit of this to be 7, but that's impossible. The last digit of this will always be 2. So k will never be equal to 5. So let's try this now with k equals 6. So this gives us that n squared will be 100 m squared plus 10 times 12 m plus 36. And so I end up with 12m plus 3 here, plus 6. And so now I need the last digit of this number to be a 7. So the last digit of 12m plus 3 is 7, which means the last digit of 12m is 4. So what values of m could I have here? This gives me that m is equal to 2, 3, 4, 5, or 7. Yeah. Okay, and this gives, in the end, that n is equal to 26 or 76, both of which we've already confirmed when squared end in a 76. And I'm seeing now that how this and how the rest of this problem is going to work out. For k equals 7, 8, or 9, it's not going to work, and here's why. For k equals 7, 8, or 9, we have n squared is equal to 100m squared plus 10 times 2mk plus k squared. Okay, so 7 squared is 49, 8 squared is 64, 9 squared is 81. The tens digit of all of these is even. And so when I write k squared as its, if I break it up into its digits, I want to carry the tens digit into this term here. But that'll always be an even number for these values of k. And so the last digit of this, when I include the tens digit from here, the last digit of this can never possibly be a 7 because it has to be even. So our final answer here, if second last digit is 7, then the last digit must be 6. Because up to 100, if I look at all the squares up to 100, the only ones that have a 7 in the tens digit are 24, 26, 74, and 76. That's an exhaustive list. And because we're only concerned with everything mod 100 here, we only need all of the squares up to 100. Thanks for watching.